So I'm going to walk through my solution to Exam1 Problem 5. So for this problem, we're given a op-amp circuit and we're asked to find out about the transfer function. The transfer function is defined as V out over I in. So I have drawn the circuit here. So this is the circuit that we are going to analyze. For part A of the problem, we are asked to determine the transfer function if op-amp is ideal. So we first list out a few characteristics of an ideal op-amp. Gain goes to infinity, input resistance goes to infinity, output resistance goes to 0, and also we have the property that V plus equals V minus, and since V plus is grounded, we also know that V minus is equal to 0. And also the property that I in and I plus should be 0, so no current going into the op-amp. And then we can set up a relationship between V out and I in. So V out minus V out minus V minus over R is the current here. It's the current in this direction. So since I in is defined in this direction, which is opposite of this current, so we have a negative sign in front of I in here. This current is equivalent to this current because there's no current going into the op-amp. So by rearranging this this equation, V minus is 0. So by rearranging this equation, we get V out over I in equals minus R. For part B of the problem, we are asked to determine the transfer function if the op-amp has a finite internal gain. And we're also asked to draw the schematic with the op-amp replaced with the dependent source model. So I first draw the circuit with the dependent source model. So notice that the polarity of Vx here, it is negative on the top and positive on the bottom because we have to be consistent with the setup of the circuit here. So positive is connected ground. We also have positive connected ground here. So we can set up this formula by simply analyze the circuit. So negative Vx, so the voltage here should be equal to the voltage here plus the voltage across here. So negative Vx equals V out plus I in times R. It is plus I in times R because I in goes to here and then it will travel here and finally here. So it will go this direction, which means that the polarity of the resistor is this way. So that means if we add the voltage in this direction, we are actually adding the voltage. So we have a plus sign here. And if we are only having this equation, we have two unknown variables in one equation that we cannot solve. So we need another equation to help us solve the system of equations. So we have another one here, V out equals A in times Vx. So because they share the same node, they should be of the same voltage. Plugging in this equation back to here, we get negative V out over A in equals V out plus I in times R. And we do some rearranging of the formula we get down here. So negative I in times R, because we move it from here to here, we have to have the negative sign. So move this one here, we have the positive sign. So we have HS equals V out over I in. By moving the I in here to the bottom, and the 1 plus 1 over A in to the bottom here. So we have it this way, and we can further simplify the fraction by multiplying the top and bottom by A in, so we get this form. And then we can perform a sanity check to see if our answer makes sense. So we take the internal gain, we take it to infinity, and we find out that HS actually goes to negative A in times R over A in, because we can ignore that one term because A in will be significantly larger than 1, so we can ignore it. And this term will evaluate to negative R, which is what we find the gain to be if the gain of the op-amp is infinity. And for part C of the problem, we are asked to we're given that R equals 1k ohm, internal gain equals 10 to the 5th, and the GBP equals 10 million, and we're asked to determine the approximate 3 dB cutoff frequency. So to find that frequency, we have to first have the HS function actually in terms of S. So from part B, we have HS in terms of A internal, but a more realistic model of the gain of op-amp could be derived with this formula. So AS equals A internal times the breakoff frequency of the op-amp over S plus omega B. So we replace every instance of A int by AS, and then we simplify the equation by multiplying the top and bottom by S plus omega B. So we get the equation here. We can further simplify the equation for our approximation, because A int times omega B should be much larger than omega B. So we can basically ignore this term. And also, we know that by definition, GBP equals to A int times omega B. So we can replace every instance of A int times omega B by simply GBP. So we get HS is approximately negative R times GBP over S plus GBP. So we have for S much lesser than GBP, HS goes to negative R, which is our passband gain. For S much greater than GBP, we have HS related to 1 over S, which means it is a low-pass filter. The gain is decreasing at a slope of negative 20 dB per decade. So we will say we have a pole at GBP. So our 3 dB cutoff frequency is approximately 10 million hertz. And I think this answer is reasonable because if we look back at the equation here, this equation, we find out that the HS will be will only be affected if a int is close to 1 or less than 1. So that means the gain will be significantly decreasing away from the passband gain if a int is close or smaller than 1. So what does a int close to 1 means on the magnitude plot? I think it means that it means 0 dB for the 0 dB for the gain, because a is a gain, and if we convert it back to dB, so 20 times log 1, which is equal to 0. So that's when the magnitude plot of the gain goes to 0 dB, and that's when the hs of this transfer function will start to get affected. So, and as we know, GBP is actually the intersection of the magnitude plot, the intersection between the magnitude plot of the op-amp gain with the x-axis. So the point here will be the GBP, so the frequency here. So this is when a goes to 0 dB, which means actually the actual value will be 1, which the hs of this transfer function will start to get affected. So I think it's reasonable that the cutoff frequency of this hs function is actually GBP 10 million hertz. Okay, thank you.